Hey, so welcome to another video. Today we're looking at something called the exponential form of complex numbers and also something called Euler's formula to do with complex numbers, which some of you may or may not have heard of before. It's certainly a very interesting result. So let's get on and start looking at it. And we'll start by looking at something we're already familiar with, the polar form, or another name for it, the modulus-argument form of a complex number, which was to say that we write it in terms of its modulus r and then its argument theta, which goes inside a cos for the real part, and for the imaginary part it goes inside a sine. So yes, that is the modulus and theta is the argument. Now, advantages of the modulus argument form are that it's very easy to instantly read off from this form what the modulus is and what the argument is, but also it's very easy to convert back to Cartesian form of a complex number, because all you need to do to get the real component, for instance, is just to multiply the r by the cos theta and also the r by the sine theta to get the imaginary component, which is useful if you're having to do any adding, because adding is easiest to do when you've got it in Cartesian form, because you just add the real components and add the imaginary components. But what about multiplying? Well, it is actually easy to do multiplying when a complex number is written in modulus argument form. However, you've got to remember a little trick when doing that, and that little trick becomes a bit more easy to spot and remember, and feels a lot more intuitive when we write it in another form for a complex number, and that form is the exponential form of a complex number. So, what is the exponential form of a complex number? It is r lots of e to the theta I, where once again r is just the modulus of that complex number and the argument is theta going in that power next to an I. So, what are the advantages of exponential form? Well, for a start, it tells you all the same information that polar form does, but it takes a lot less effort to write. So it's often quite popular, quite a popular way of writing complex numbers, because it takes so much less time to write than writing the r, the cos, and the sine all together like you have to in modulus argument form. But it also brings home some useful facts and interesting results, which start opening whole new worlds and doors, because let's start off by looking at, for instance, the number 3, the real number 3. Okay, now if we wanted to write the real number 3 in exponential form for a complex number, because the modulus of 3 is just going to be 3, and the argument of 3 is going to be 0, because it's on the positive real axis, so it's making an angle of 0 with the positive real axis. That means if we were to try and write 3 in exponential form for a complex number, it would be 3 lots of e to the power of 0I, because the argument is 0 and the modulus is 3. Now, good news is this result makes total sense, because we've got 0 times by I in the power, and 0 times by anything is 0. And then therefore we've got e to the power of 0, which would of course be 1. And therefore 3 to the power 3 times by 1 is just going to be 3. So it makes sense. It totally makes sense with a result or number that we're already familiar with. But then it starts becoming really interesting when we start looking at maybe numbers elsewhere on the Argand diagram. For instance, if we look at the number -1, again, at first glance, a very innocuous number. We're very used to negative numbers by now. But if we look at the modulus of -1, that of course would be 1. And if we look at the argument of -1, that would be pi, or pi radians, I should say, because of course it's all the way over there versus the positive real axis. So therefore, if we're trying to write 1 in exponential form, we're going to get 1 lot of e to the pi I. Wow. That is truly an amazing result because it connects so many important things in maths all together in one result. We've got right here negative numbers, we've got exponentials, we've got pi, which is to do with circles and trigonometry, and we've got I, the imaginary number, all being linked together in this rather amazing result. So that's pretty neat. That's pretty neat indeed. And in fact, that's just one of the very useful conversions we can do using Euler's formula. And all Euler's formula is it's effectively the result or equivalence we were writing above. Basically, the conversion between modulus-argument form and exponential form of a complex number. So Euler's formula says that this is equal to this. Now, still, what are the uses? It's certainly a neat way of writing complex numbers in a different way. But why do we care? Well, as I already mentioned, multiplying becomes a lot more intuitive if we're dealing with it in exponential form. It becomes a lot easier to see why certain things happen when we multiply two complex numbers together. So what do I mean by that? Well, let's look at an example. We've got two complex numbers here. Z1 equals 5 plus 5 root 3i, and Z2 equals 7 minus 7i. And if we wanted to multiply them together, we could already do that. Even though they're written in Cartesian form, you just got to multiply out the brackets. And then obviously simplify any things like I squared that you get out of that. However, admittedly, this is okay if you're just multiplying a couple of complex numbers together. If you're multiplying more than two, then it starts becoming a lot of effort because you're having to multiply lots of brackets together, and that's a bit of a pain in the butt. So, you know what? It would be a lot easier if we looked at these complex numbers in exponential form, because Z1, 5 plus 5 root 3i, 5 plus 5 root 3i would have a modulus of 10, and it has an argument of pi over 3. So writing it in exponential form, it'll be 10 e to the pi over 3i. And doing a similar thing to Z2, 7 minus 7i as a exponential form complex number would be 7 root 2 lots of e to the minus pi over 4i. So, why does this make it easier to multiply them together? Well, it means we can see what's going to happen to the modulus and the arguments of those two complex numbers when we multiply them together. Because if we multiply these two things together, well, the modulus numbers are out the front. And therefore, if we want to do Z1 times by Z2, all you've got to do is start off by multiplying those two modulus numbers together. Okay, and then what about the arguments? Well, the arguments are in the powers of the exponentials. And the thing is, we know what happens if we multiply two exponentials with the same base together. By index laws, we of course just add the powers together. So if you're wanting to multiply two complex numbers together, all you've got to do is add the two arguments together. Now, of course, because I got a negative argument for one of them is a plus minus, which of course becomes just a minus, but we're still adding the arguments together there technically. And so therefore that means very simply the result of multiplying these two complex numbers together is two very easy calculations. It's just going to be 70 root 2 lots of e to the pi over 12 I. And there you go, that's it. So in fact, in general, you can say that if we're multiplying two complex numbers together, then the result would be the sort of the product of the two modulus of the two complex numbers, and also the arguments added together. So if we're writing it in modulus argument form, it'd be written like this, and therefore also, as I already pointed out, if we wrote this in exponential form, it's just something like this. Cool, so that makes it a lot easier to multiply complex numbers together, particularly if you're doing lots of them. And also, this idea of adding several arguments together within a cos and within a sine will become very useful in a future thing that will be either in a future video or in a future class, depending on when you are looking at this video. So there you go. That's a cool result. There's one last thing I want to look at in this video in case you're interested in, and it's the fact that we've already mentioned what Euler's formula is. We mentioned that it was this result here. And it's all very well me saying, yes, it's true, but it is a bit weird, and it is, it's not always nice just being told things and just having to accept them in maths. It's nice knowing why, or having some sort of beginnings to a proof so you can wrap your head around it. Now, I'm not going to do a full proof here because I would prefer to do that in a full video sometime. And in fact, one of the ways of proving it would be better done after you're familiar with something known as Maclaurin series. So I'm sure there'll be a video at some point showing this proof using Maclaurin series once you've covered it. But for now, a sort of very oversimplified, it wouldn't count as a full proof, but a small sort of hint at a proof can appear here. What I'm going to do is I'm going to use a sort of property or use of differentiation, which is that when we differentiate different things, they tend to have a rather unique result for each thing that I'm differentiating. For instance, if I differentiate x squared, it just becomes 2x, which therefore means if I'm going from the original function to the derivative, all I'm doing is I'm square rooting and then timesing by 2 for this particular function. But if I look at different functions and differentiate them, going from their functions to their derivatives will have a different action needed to happen. For instance, if I want to go from, we could say, x cubed to its derivative, we've got to cube root, multiply by then square, then multiply by 3, which is again a very different action to the action we took for the x squared. And then lastly, just to hammer home the point, e to the 4x, if I differentiate that, I get 4e to the 4x, and therefore, for instance, going from this function to its derivative, all we've got to do is we've got to multiply the original function by 4. So therefore, it kind of could be viewed that most derivatives should have a rather unique sort of almost calling card, if you will, to show that something has happened when we have differentiated them. So that means that if we are going to now differentiate e to the xi, that should also have its own unique result. So let's have a look and see what happens. If I differentiate this, we know it should differentiate. If we apply the same rule as if I was instead just a real number, it should in theory differentiate to this. And it does, because I is a number, although it is an imaginary number, it is still a number, and still therefore the rules from before apply. But what happens if we apply that rule to differentiating cos x plus I sine x? Does the same property of multiplying by I, going from the original functions to its derivative, still happen? Let's have a look. So if we differentiate cos x, that's going to differentiate to minus sine x, if I can say the word differentiate properly. And sine x differentiates to cos x, so we're going to have a plus I cos x. Okay. Now, so what? At the moment, nothing really easy to see. However, the thing is we can rewrite this second function. We've effectively got minus 1 lots of sine x, and we should be familiar with the fact that I squared is equal to minus 1. So in reality, we actually have, it could be viewed as I squared lots of sine x. But wait a minute, that means I now have got a common factor of I that I can factorize out. And therefore, that means that yes, once again, the original function just has to be multiplied by I to get the derivative, which is exactly what we got here as well when we differentiated the exponential. So that seems too much of a coincidence for it to be just by chance, and it kind of hints that, yeah, you know what, this thing we had going on up here with Euler's formula is probably true. Now, as I said, that's not a proper full formal proof, but it should at least be giving you the hint that, we do have something useful going on in here. And this relationship between exponentials and cos plus I sine theta is a relationship we're going to be using to our advantage heavily moving forward. Okay, hope you found this video interesting. I will see you probably in a future video. Thank you and goodbye.